Hi folks, welcome back to Physics with Captain Rod. Making this video to be an introduction into the theorem of work and energy. Now first of all, I'd like to chat a little bit about the term theorem. In mathematics, a theorem is something that is provable beyond all shadow of a doubt. If you find one counterexample, it's not considered a theorem and thrown out. Physics has to be a little bit softer in how things are defined. The work-energy theorem is called a theorem because no counterexample has ever been found, and I doubt one ever will be. But you can't prove this per se. There's no proving it. We're going to treat it like it is a theorem, and it's one of the most important concepts in all of physics, the work-energy theorem. So let me chat about the picture and what we're looking at. So for starters, imagine we have some object here that has an initial velocity vector to the right. I'm going to restrict this to one-dimensional motion. However, the work-energy theorem does apply to 2 and 3 dimensions. It's just easier to visualize and go through the math in 1D. And imagine that there is a force applied to this object, which is to the right. So that's going to make this object accelerate to the right. So its velocity vector is going to be get a little bit larger. We're going to imagine in this example that this force is constant, not changing, and applied throughout this entire process. So what we're going to do is we're going to take a look at what happens when this force is applied over a distance delta x. Now, the first important equation to apply here is Newton's second law. Newton's second law is the basis for all of what's called classical physics. So I'm going to go ahead and write this out. Force is equal to mass times acceleration. That's Newton's second law. So that's this force is equal to the mass of our object here times its acceleration. Now, I want to see how work is involved. Well, you'll notice there's a force here on the left. I can turn this into a work term by multiplying it by the distance delta x. So I'm going to do that. Force times delta x equals. Now, if I multiply the left-hand side by delta x, I also have to multiply the right-hand side by delta x. The left-hand side is now the work done by this force. Now, the right-hand side, I'm going to play around with a little bit. Acceleration can be written delta v over delta t. Let me write this off to the side. Delta v over delta t. Delta v can be written v final minus v initial, and then over delta t. So I'm going to go ahead and write this term right here. V final minus V initial over delta t. And then the delta x I'll go ahead and just leave alone for a moment. Now, if we group these terms together, delta x over delta t is what we call the average velocity. And as long as your acceleration is constant, and in this case it will be because I've assumed constant force, then the average velocity is literally the average of your initial and final velocities. So I'm going to go ahead and write that v final plus v initial over 2. So this equation now can be written m v final minus v initial, that's for this term. The delta x over the delta t is equal to the average velocity, which can be written v final plus v initial over 2. Now, let's see here. The half and the m, these are both constants in this problem. I'm going to kind of bring those out in front. 1/2 m, and the top of this can be multiplied out. So we've got v final minus v initial times v final plus v initial. If you go ahead and multiply that out, what you get is v final squared minus v initial squared, because the outer and inner terms are going to add to 0. This outer term is plus v final v initial, and this inner term is minus v final v initial. And I'm going to go ahead and separate these out. 1/2 m v final squared minus 1/2 m v initial squared. So this equation is now saying the work is equal to this expression, Well, these terms, 1/2 mv final squared, 1/2 mv initial squared, these are what are called kinetic energy terms. In general, kinetic energy is calculated by taking 1/2 mass times the velocity of a system squared. Because in this part of the equation that's a final velocity, this term is what we would call the final kinetic energy. And because this is an initial velocity, that makes this term an initial kinetic energy. So conceptually, what this equation is saying is the work done on the system is equal to Ke final minus Ke initial, which is equal to the change in kinetic energy of the system. So what's happening here is that when there's work done on the system by this force, we are changing the kinetic energy of the system, and the work done is identically equal to that change in kinetic energy. So what that means, let's say this force does 3 joules of work positive, then the system's change in kinetic energy will be exactly 3 joules positive. Now, I'd like to take a moment and kind of rearrange that equation a little bit and show you how I like to write the work energy theorem. Oops. Just want to make myself some room here, not get rid of everything. Okay. So again, kind of picking it up from here. The work is equal to this term, Ke final, minus this term, which is Ke initial. I like to rearrange this equation and put this thing on the left-hand side. So we've got the initial kinetic energy of a system plus the work done is equal to the final kinetic energy of the system. This is how I usually express the work energy theorem. It's a very, very powerful theorem. It allows us to relate speeds. So if you look at this term has got a 1/2 mv squared in it. Work terms are all force times distance terms. Final kinetic energies are all 1/2 mv squared terms as well. So what this theorem will allow us to do, among other things, is relate initial speeds to force and distances to final speeds. In upcoming videos, I'm going to expand this equation some to also include potential energies, but the work energy theorem as it sits, that's it right there. Theorem of work and energy says the initial kinetic energy of the system plus work done on it equals your new kinetic energy. I hope this video introduced you to this theorem reasonably well. Have a great day.